Okay, so let me perhaps, what I will do next is, assuming that the right condition for these operators is that they are topological, perhaps better said, assuming that these are indeed topological operators, something I will show in this lecture, but let's take this assumption for a second. Let's try to understand what this picture implies. Right, so if my operators are topological, something that, as pointed out before, was already half assuming when I wrote that picture, then I can redraw the picture in the following way. It's perhaps a bit more provocative. So I'm going to put my operator O here, and then my operators UG. I was asked to write a little bit bigger for the back. I will forget during the week, so please do remind me and don't mind. Okay, so I'm going to deform my operators in the following way. So remember that I can deform them as long as I'm away from a charge operator. I have a charge operator here. So the idea is that I'm going to bring them on top of each other. So this is still UG, and this is still UG dagger. But in this way, that they collapse to being on top of each other almost everywhere, except close to O. Now, using that UG is equal to UG dagger, so let's unpack this. This is e to the I GQ, and this is e to the minus I GQ. So clearly, if I multiply them, I get the identity operator. Huh? Thank you. I was thinking of the abelian case in here.
No, but UG on the left, it should be UG inverse.
Well, so let's think about the abelian group. Let me use alpha here. Right? So this is U1 seen as R mod Z. The abelian structure here is addition. So the inverse of alpha is minus alpha. So that's what I wrote minus G, because I had the abelian group in mind. You're right, there should be G inverse. Let me correct it by going to the abelian case.
Yes, but there's no inverse on U.
I'm taking the dagger?
Yes, and that's equal to the inverse.
Yes, yes.
Yes, but you don't.
Oh! Sorry. Yeah, lecturing for more than 2 hours in a row is not a good idea. Yes, you're completely right. Thank you, thank you. Yes. So yes, what should I say? This is equal to this, and this is equal to this. And this is equal to U minus alpha, which is U alpha inverse. Thank you. I think now everything is correct. Yes. So, completely right. Yeah, thank you. So the point is that indeed these two things will cancel each other. This will be the identity. So this picture can be written in the following way. I have an operator O in here, and all that's left is an operator that locally is like UG and it surrounds O. And now I know from my original relation here that this is equal to the other. This is the representation of G acting on O. So I can isolate this picture. This will be the way that symmetry generators act on operators in the Euclidean picture. If you have some operator, UG, and in this particular case, UG is codimension 1 in space-time, so it'll be associated to some 3 manifold. So UG will be mapping some M3. And if you're in 4 dimensions and you have a 3 manifold like this, which I will assume is orientable, you have an inside and an outside. So if your operator is inside, then this is the same thing as RG. So I could write this as UG on M3 and an operator. Okay. So this will be the basic way in which operators act on each other in the context of generalized symmetries. The thing I will generalize is that O will no longer be at points, and therefore this U will no longer be in a 3-dimensional manifold. So this will come in a minute. Okay. That's a good point to ask. How many of you have seen differential forms? Okay, that's... How many haven't seen? Sorry, this is the embarrassing. Who hasn't seen differential forms? Okay. Because some people that didn't raise their hands, one or the other, I will assume they have seen differential forms. So my review of differential forms will be extremely fast, just to set a couple of conventions that I need. And maybe one theorem that maybe some of you haven't seen. So say that I have a P form that will write like this. And one thing that I have is that omega P wedge omega Q is -1 PQ. So I have an antisymmetric product. I have a differential. That acts nicely on the product. All right, so that's standard. And the thing that's perhaps a little less standard is that we have an integration. Let's say D satisfies that D squared is equal to 0, of course. And the thing that's a little bit less standard is that I have a Stokes formula. So say that I have a fibration. So I have a fiber, some total space X, and some base B. Does everybody know what a fibration is? Yeah, good. So you have a fibration, then there's a Stokes formula, which tells you that D of the integral on the fiber of a P form is the integral on the base. No, that's it. Is the integral on. Yeah. Yeah. Omega plus or minus plus -1 to P minus the dimension of F, the integral on the boundary of F of omega. Okay. So the Stokes formula is familiar to everybody in this form. I'll need it for fibrations. So the thing that's perhaps more common is the case in which the fibration is the trivial fibration over a point, in which the base is a point, in which case this part here vanishes. And then you have the formula that tells you that 0 is equal to the integral over the fiber of d omega minus, this is a minus in that case, the integral over the boundary of the fiber of omega. Okay. All right, so one thing I haven't done so far is to show, sorry. Apologies, and I forgot one thing. There's a Hodge star, of course, which maps p forms to n minus p form, where n is the dimension of the spacetime. And it satisfies that if you act twice with a Hodge star, you get a sign, which is p m minus p times the signature, well, say, times plus or minus 1. And plus 1 is for Euclidean, and minus 1 is for Lorentzian. Okay. Right, so one thing I haven't shown so far, I did it for the classical theory, but I didn't do it for the quantum theory, that U was indeed topological. Basically proved for the classical theory that Q was invariant under time translations, and then I waved my hands, and you believe me. Or some of you perhaps didn't believe me. But we can prove this in the quantum theory without too much trouble. So let's do the following. Let's assume that we have a symmetry so this is a transformation of the fields. Again, here I have to assume that I have fields. If I don't know about fields, I have to figure out the topological operators independently. That's what I'm going to do towards the end of the week. But for the moment, let's assume that we have fields. And what does it mean to have a symmetry in quantum field theory? It means that if you take the product of the measure times the action, this should equal the transformed action and measure. That's the statement of having a symmetry. And I'm going to do an argument which is very similar in spirit to the thing I did classically. So assume furthermore that phi prime is some phi plus some alpha variation of phi. And this is a symmetry for any alpha. So you have a continuous symmetry. Now promote alpha, which is a constant, to some alpha of x. This is a standard trick, something I already alluded to when I was discussing Noether's theorem. In that case, what you have is that, first of all, you have defined a new phi prime, which is phi plus alpha of x variation of phi. Now, this is not going to be a symmetry. Right? For generic alpha of x, this is not a symmetry, no reason it has to be. But the thing it is, it's a redefinition of the fields. I can do the path integral with respect to this field, I can do the path integral with respect to this field, because I'm assuming over all fields anyway, I should get the same answer. So one thing that should be true is that the path integral over these fields should be equal to the path integral without the primes first, over the prime fields. So this is true because I sum over all fields. Right? All right. But if this is a symmetry with alpha constant, it means that this bit, just the measure times the action, should be the same whether I use phi or phi prime. So it must be the case that this is the integral of phi e to the minus s phi times something that is the identity whenever alpha is constant. So this has to be of the form integral of d alpha, which something, I'm going to call that j, over your four manifolds. If you remember in the classical case, I showed to you explicitly, or more or less, I left it as a little calculation after I showed, that this is indeed what happens if the measure is invariant. Right? The action was not invariant, but it changed by total derivative of the parameter. So the logic here is the same. I'm writing the most general expression that vanishes when this is constant and has the right transformation properties. I don't know what j is at this point. It is whatever it is. One thing I know is that because alpha is a function, some arbitrary function, this is a one form, and therefore this is a three form. Okay, so this is equal, integrating by parts. And here I'm assuming that the behavior at infinity is sufficiently nice. So either M4 is closed, or perhaps it has a boundary, and I'm setting the fields to 0 on the boundary, or maybe they decay fast enough if M4 is non-compact. In either case, assuming that I can forget about the boundary contributions, this is if I this is 5, 1 minus integral of M4 alpha wedge dj. Now, all these things are equality signs. They're true for all alpha. And clearly, the first term here is the first term I started with. So this thing has to vanish for arbitrary alpha. So I have that alpha is arbitrary. So you could take a bump form, for example, something localized around the point in space-time, if you like. And this way, you conclude locally that dj is equal to 0. So this is a quantum derivation. This is known as a word identity. Or perhaps I'm being a little too general here. This is the conservation of the nether current in the quantum theory. I will generalize it in a second in a way that allows for the presence of charged operators in this path integral. So everything I said is for this specific path integral. I'm going now to introduce charge operators and see what happens. Any questions so far? Right, so say that we have now with charge operators. So let's say that we have the same path integral of d phi, some action, and then some operators. That I insert at some points. I'm going to call these points y1 to yn. Okay. Any questions so far? All right. So under a symmetry, the operators will generically transform. So OI will go to OI plus some transformation parameter. Let me call it alpha as before, variation of OI. Okay, so same argument as before. I can do the path integral in the new variables, the phi prime, shifted by something which is non-constant. Okay? Not going to be a symmetry, but it is whatever it is. But we know that because we are summing over all fields, the final answer should be the same. Now, the operators will also change, because the operators depend on the fields. So as I change this, the operators will change. So this will be some O prime of y1 up to an O prime n of yn. So how does this change? Well, we know that the measure times the action is invariant if alpha is constant, as before. That was our starting assumption. So the change in the measure times action is going to be, as before, a term like this. So the integral of d phi e to the minus s phi 1 minus integral alpha wedge dj. But the fields will also transform in this way. So what do we get? We get the sum from 1 to n of the first order OI, sorry, O1, Y1, up to OI minus 1. Sorry. Yeah, no, it's fine. I minus 1, OI plus alpha delta OI times OI plus 1, Y I plus 1, ON, YN. Okay, that's a bit of a mouthful, but hopefully it's clear. What I'm doing is taking the variation to first order, and that means that the sum of the variations of these things to first order. So I vary each field. So the thing I'm summing over is this, the variation of this one, variation of this one, all that. Yep. Everybody with me so far? Yeah, good. All right, so the first order. Well, clearly the thing to zero order just cancels with the original expression. Right? And I'm left with these terms in here. So this term with the alpha here, and this term with the alpha in here. So what do you get? That the integral of alpha wedge dj has to be equal to the sum over I of O1 by 1, I minus 1, times alpha. Yep. Okay, so almost there. Here I have an integral. Here I don't. But I can introduce integrals by introducing delta functions. So I'm going to write the integral of alpha. Some could be outside, but outside. By 1. And then when it comes to this one, I'm going to introduce the delta function there. So that's delta of x minus, so x is the position in the manifold where you're integrating, the integral is in x. And that's the delta function. All right. Sorry, I mean two things by delta function here. This is a Dirac delta function. This is a variation. Apologies. Both notations are standard, but variation of yi. Right? And now, as before, because my alpha is arbitrary, I could choose it to be a bump. Yeah. This one? Yeah. But I have the Dirac delta here. So I could choose, but yeah, let's put it if you prefer. Yeah. Doesn't really make much of a difference. All right, any other questions? All right, and now, as usual, as in the previous version of the argument, without the operators, my alpha is something I can choose. It's a function of x. I could choose it to be bump form around the point. So I can get rid of the integral. This has to be true pointwise. And I end up with the word identity, which is dj is equal to the sum from 1 to n of nothing I wrote there, so O1 by 1, delta x minus yy, delta y of yy. Okay, so this is the word identity in its final form. Okay. Any products? Any questions? Yeah.
You said that the integrals should be, the integrals should be the same because we're summing over all fields.
Yeah.
Are we assuming that the symmetry action is faithful? Otherwise, it might be symmetry over.
You're right. This is a Lie group. It's infinitesimally connected to the identity. So yeah, closer to identity, assuming that's a standard group, there should be no problem. Yeah. In general, yes. Yeah. Yeah. Any other questions? Yeah.
Are we assuming that the path principal measure is invariant?
We're assuming that that product there is invariant. The product is invariant, yeah. So you don't have an anomaly in the standard sense. Yeah. Very good. Any other questions? All right, so that's a version of the conservation of the current, which is true in the presence of charged operators. And I emphasize you should understand this in the path integral. Okay, if I'm computing a correlator, I can replace these currents by these expressions which have delta functions at the points where I insert my operators if the operators are charged. Yeah. Oh, yeah, thank you. Yes, yes, you're completely true. This is the J product of all the operators. Yeah. Thank you. Yeah, very good. Any other questions? Okay, so this is known as the word identity. And notice that here I didn't use a classical approximation. I think this is an exact identity in the path integral. Okay, so now I can rephrase some of the things I said, at least in the case I have another current in a much nicer way. So originally my U, the William group, U alpha, it was integrated over R3, and it was the integral over R3 of J0. I can understand this as the integral over R3 of J mu times a normal vector to the surface. And I suppose I here should write D3x and D3x. Now the normal vector of a space like a slice, that's time-like, that's why I'm picking the J0 component in here. But now in the language of differential forms, this is nothing but the integral on R3 of J as a differential form. And here, up to conventions, I'm mapping between J and J mu in the following way. So J is a differential form defined in the following way. It's 1 over 6 J mu epsilon mu mu rho sigma dx nu dx rho dx sigma. The details are not so important. But the important thing is that once you take a combination like this, the 1,6 is not very important, but the structure is important in the sense that this is a 3 form, and this 3 form was precisely the one that appeared in our word identity. So one thing we know is that dj is 0 if there are no charged insertions. Okay, so now we can start deforming this operator in a much easier way than we did before. Before I had to wave my hands and talk about T mu nu and so on, but here I can be completely explicit. So say that you have this insertion of this operator in the path integral. So this is U alpha e to the I alpha integral of J over some 3 manifold M3. Let me call it M, no, M3. Can you see from the back? Sorry, I suspect I'm going too small. Is it okay? Yeah, thank you. All right, so let's consider this surface. Say that I'm wrapping my original operator U in some 3 manifold. It could be R3. And now consider a little deformation of this manifold. I'm exaggerating it for effect, but this is a continuously connected deformation, as small as I like, or as big as I like, as long as it's continuously connected. And this gives me a new manifold, which I'm going to call M prime. So let's compute, and let's assume that there's no charged operators in here. So I'm going to call the inner part here B, and this is a 4 manifold. So the property is that the boundary of B4 is, with some choices of orientation, M3 minus M prime. All right, so let's do the following. I'm going to compute U alpha on M3 times U alpha in M prime dagger. This is the kind of thing I was doing before when I was trying to isolate the action on an operator. All right, so this is the integral of e to the alpha on M3 of j minus I alpha on M prime. This is the integral, sorry, the exponential of I alpha M3 minus M prime on j. Now M3 minus M prime, this is the boundary of P4. Now I can use Stokes. So this becomes the exponential of I alpha in B4, d of j. But of course, this is the identity, because dj is equal to 0. Right? So this is a proof, now at the level of the path integral. Here I didn't do any assumptions about classical limits, that my operators have to be topological. At least these operators which are constructed out of another current. All right, let's do one more, just to play with these ideas. You might not have the final configuration. I have my abelian operator, U alpha, and some S3. And there's an operator inside, O of charge Q at 0. All right, so if I put this inside the path integral, right, these two operators like this in the path integral, and then I take the integral over my fields with some action. I can use my word identities, but now I have to use the word identity in the presence of operator insertions. And in particular, these charged operator insertions. So the word identity in this case was that dj, I have a single operator, so this is dj times O is equal to the variation of O. This case is very easy because I have a single term in the sum, so that's like it. And now I have to be a little bit careful. This is together with some delta function at the position of the operator. So if the operator is at 0, this is a delta function at x. Right? So, very good. Now I use the second fact, that the S3 is the boundary of a 4 ball. So B4 is the inside here. And I have all I need. So let's see. This is the path integral phi e to the minus s phi, my operator, e to the minus, sorry, e to the I alpha integral on S3 of j. There we go. I turn the S3 into B4, writing this as a dj. And now I know that whenever I have a dj and it's hitting an O, I get the variation of O, which in this case, because this is of charge Q, is going to be QO with an I. And the delta function that localizes the integral at 0. So this is going to be the integral of d phi e to the minus s gamma, maybe the method of expansion explicitly, O 1 plus I alpha integral of dj, I alpha over 2, so squared over 2, integral of dj squared, and so on. And now I can replace any of these O times dj with IQO delta. So if you work out through the details, this is going to be the integral d gamma e minus s theta of t to the alpha q. And oh, there you go. So this is the expected action on the operators inside the path integral. We started at 1/4 I think. Is that correct? No. Oh. At 11. Okay. So I have 45 minutes left. Ah, okay. So I have 1 hour left. Very good. That's reassuring. Yeah. Yeah, I use the word identity in there. The word identity is a statement that's valid inside the path integral. So as I'm computing correlators, I can replace, whenever I find this dj of O, I can replace it by this variation times the delta function, which is what I did. Now, the thing you can do is take the d outside the path integral, if you want, and write this as a correlator, which is a form which is often found. So you can write this like this, djx of O equal to variation of O delta x, something like this. And that you can do, that's also true. Okay. Any questions? Okay, so let me start with, this was all classical symmetries, but now we have enough understanding of classical symmetries that we can start generalizing to generalized symmetries. Oh, yes, sorry, yes. Standard, yes. These are all these symmetries. The second part of the lecture so far was quantum. And yes, and what I mean is, now I'm going to do things that are not so standard. So the basic idea so far we learned that symmetries, well, there's continuous symmetries, but more generally, symmetries induce topological operators. So the basic idea of the modern understanding is trying to invert this arrow. I'm going to declare that I'm going to think of every topological operator in my theory as a symmetry, and I want to see which things survive and which things don't. Of course, the power of a definition is how useful it is. And the thing we will see is that many of the familiar concepts in this kind of standard symmetry survive if I make this identification. Many of the things don't, but sufficiently many things survive that this identification is useful. That thinking out topological operators in quantum field theory as symmetries is a very useful organizing principle. So the task, once you believe this philosophy, or once you want to verify this philosophy to see if this makes sense, is you want to identify all topological operators and you want to see how they behave. So the whole field of generalized symmetries is basically trying to answer this question in increasingly realistic theories. And one of the hopes is that by thinking out topological operators that don't quite fit in this standard framework, we'll learn new things about quantum field theory. We have already learned a number of things, and I'm confident that there's many more things that we can learn. Okay, so two things that you realize right away. There's no good reason why topological operators need to be three-dimensional. And they do not need to form a group. Okay, so two of the basic things that I was assuming in the previous lecture, they don't really have to happen. So I'm going to start by studying topological operators that do form a group, but are not three-dimensional. These are known as higher form symmetries. And later on in the lectures, I will go to some operators that do not form a group. So what's a higher form symmetry? The definition, I should say, these were introduced systematically in this very nice paper that I encourage everybody to read, in a paper by Gaiotto, Kapustin, Cyber, and Willett, 2014, I think. And how did they define higher form symmetries? They were concerned about topological operators that form a group, but they are not necessarily three-dimensional. So the basic idea is we want to study topological operators. Yeah, topological operators, where the charged objects are p-dimensional. So for ordinary symmetries, my charge objects are local operators. They live at points, and therefore they have P equal to 0. Ordinary symmetries are zero-form symmetries in this more general language. Okay, so let's do some counting. What we would like to have, basically, is a picture analogous to this one. In the ordinary case, I had a point which was surrounded by a manifold of codimension 1. So this manifold was a 3D manifold in 4 dimensions. But it's a bit nicer to think of this as a codimension 1 manifold in space-time. The fact that it's 3 dimensions is specific to 4 dimensions, but the fact that it's codimension 1 is general in any dimension. If you want to take something that surrounds a point in d dimensions, it has to be codimension 1. In fact, what I drew in the board is not really a 3-dimensional manifold, it's a circle. So this is a 1-dimensional manifold in 2 dimensions. It's indeed codimension 1, and it surrounds a point. In general, you can link. Link is this kind of operation that you have an inside and an outside, and you cannot contract this without intersecting. I'll give the precise definition in a second. You can link p-dimensional manifolds using codimension p plus 1 manifolds. So what's the idea? Well, we'll have a word identity, just like the one we have here. But the delta function will not be a delta function localized at a point. It will be a delta function localized in the p-dimensional manifold where my operator lives. So if I want to have the same sort of calculation I just did, where I try to contract this by encounter delta function, and from there I get the variation of the field, I need these two things to link. So finally, what's linking? So if I have a manifold here A and a manifold B, B links A if B is the boundary of some C and C intersects A. So the idea here is to think out the space of deforming this, gives you some sort of disk in this picture. This disk has boundary B. And as I contract, at some point I will intersect this manifold. And this is where the word identity happens. That's where this operator transforms. Okay? So this implies, well, let's see, if C intersects A, that means that the dimension of C plus the dimension of A, is the dimension of your spacetime, T. Now, if B is the boundary of C, it means that the dimension of B is the dimension of C minus 1. So this implies that the dimension of B is D minus the dimension of A minus 1. Now, by definition, the dimension of A is P, so it's D minus P minus 1. So if I'm measuring P-form symmetries, that is the symmetries that act on these extended operators of P space-time dimensions, I'm after operators, topological operators, which have dimension D minus P minus 1. Or equivalently, the codimension is P plus 1. Okay, so this proves this statement here. Right. One of the things I should say is that in the case of ordinary symmetries, the non-abelian case is, of course, very important. In the case of generalized symmetries, they are up to some subtleties that I don't want to explain today, but they might come later in the course. They are almost always abelian. And that means that I can basically do what the analysis wants for one theory that has an abelian symmetry, and every other system will behave in the same way. So let me do an example, and what I'm going to do is to take this example. It's a free theory. It's a theory that I can understand from beginning to end. I'm going to beat it to death. I'm going to understand everything there is to understand. And with that, I basically understand the general case. So my example is going to be U1 Maxwell theory. And I'm going to do it in 4 dimensions. This is a theory that has an action, an Euclidean action, which is, in my conventions, 1/2 E squared, integral of f wedge star f. Now you can generalize this to include the theta angle. I'm not going to do that. I don't want to complicate my life too much. But an exercise for you. Is to generalize everything I say to the theta different from 0 case. I'll try to cite references as I go that tell you how to do this exercise. Okay? Sometimes not obvious, but most of the time it's just a bit more algebra. All right. Any questions so far? One thing that is important is that this is a free theory. I should be able to solve this exactly. This is different from a non-abelian theory where I have to think harder, but this one is definitely something I should be able to do. Right, suppose my symmetry. Locally, forgetting for a minute about topology, I have that F is equal to dA. So A going to A plus lambda is a symmetry. Oh, yeah, sorry. Yes, thank you. So far, I'm not choosing a manifold. This is general. Yeah. Sorry. Implicitly, in most of what I say, I will take the manifold to be closed. But otherwise, some general manifold. Doesn't even have to be a spin, but I'm going to take it to be a spin because otherwise there's some annoying factors of 2 that I want to get rid of. Yeah. Yeah. No, I mean that. I'll come back in a second. This is not a gauge transformation. So that's part of the, if it was a gauge transformation, I would be saying something that we all know that this theory is gauge invariant. That's true. But I want to obtain a symmetry. And this transformation, as long as lambda is not a pure gauge transformation, will act on the operators. Gauge transformations don't act on the operators of the theory. Yeah, I'll come to that in a second.
Shouldn't we assume that lambda is closed if we want to have something about it?
That was literally my next 3 words. Yeah. If the lambda is equal to 0. Yeah. Okay, so very good. These 2 questions are very important to understand what's going on. First of all, I want this not to be a symmetry, but I want it to be closed. So let's try to understand the space of closed forms which are not symmetries. And for that, first we have to understand which closed forms are symmetries. So lambda is a gauge symmetry if lambda is equal to d alpha. In this case, I have gauge symmetry. But this is not the only case in which lambda is a symmetry. And here I'm being a little bit pedantic. So when I write this, I mean that alpha is some globally defined function. You have a globally defined function and you take d of that, you certainly get something that when you shift a by that, you get a gauge transformation. That's the standard thing. But that's not the only gauge transformation. It's a factor of I. Sorry. Okay, more carefully, gauge transformations are things of this form. Right? The way the connection transforms, in general, under the gauge transformation, is that A goes to G minus 1 AG minus I G minus 1 DJ. All right.
You did not specify the next one, but it should have no trivial step on
Not really. Why?
You didn't specify the next one, but the next one you are doing this
Yeah.
should not have trivial step on the homology, right? Because
Mhm.
this would be trivial in some sense. Because of
I'm trying very hard to avoid the words cohomology until my third lecture. You are right that there's a condition in the cohomology of the manifold for when this is more general than this, if that's what you have in mind. And I'm going to state it in a second. It's not in the second cohomology, it's in the first cohomology, but yes. Yes, I think so. We can discuss that. I'm going to write the formula in a second. And let's see if you agree with the formula. All right. Maybe we're thinking of different coefficient rings. That could be my possible. Yeah. All right. Anyway, without saying the words cohomology, this is the general statement, right? I have some map G from my manifold to U1. And by considering maps of this type, sometimes I can construct things that are more general than this one, but they are still gauge transformations. So here's an example. Say you have an S1. Inside M. And choose the map G, restricted to this S1, to be e to the n theta of the stack. Now, if this one is not topologically trivial, that's why I thought it was H1, then this gives you some winding numbers that you can construct. Notice that this is not of this type. Theta is not globally defined here. So I cannot construct a function of this type, but I can still construct that. Right? So in this case, implies that lambda is, if I get the factors right, so I have the integral over S1 of the thing there, minus I G minus 1 dj. I cook up the signs and so on, such that this is nicely real. This is n times the integral on this S1 of d theta, and this is 2 pi n. So this shows very clearly that this kind of transformation is more general than this one. If I have the integral of d alpha on a closed manifold, I can use Stokes. There will be the integral of alpha on the boundary. That will be 0, but I'm not getting 0. So clearly that thing is more general. So this is an example of winding. If you think of the two-dimensional language, and thinking more generally, this is also an example of a large gauge transformation. Now, people use large gauge transformation in two different ways. Sometimes they mean transformations that don't vanish at infinity, and they're physical. And sometimes they mean transformations that are not homotopically connected to the identity, like this one. I'm going to use it in this second sense, transformations that cannot deform to the identity. All right, so large-scale transformations. Well, there are things of this type. I don't have an elementary proof of what I'm going to say, so let me just state it. You can, up to gauge transformation, parameterize any connection on a bundle by holonomies. So these are going to be flat integrally quantized one forms in this case. So I just gave you an example of something that's non-trivially connected to the identity. Sorry, that's not connected to the identity, so something that's non-trivial. And now up to gauge transformation, everything is of this type. Now here I can omit, so first of all, I'm going to introduce for this the notation omega 1, so 1 forms. They have periods which are 2 pi times z. Okay. Now here I wrote flat integrally quantized because that's what I had. These were flat to start with. I wanted this to be a symmetry. Gauge symmetries are almost symmetries. Yes, they are physical. They don't change the action, in other words. But because they have this representation in terms of a gauge transformation, they're actually gauge transformations. So whenever I have a one form which is flat and integrally quantized, this is also a gauge transformation, just a large gauge transformation. So I'm going to represent it in this way. Omega 1, 2 pi z. This means that the periods of this thing are integral, times 2 pi. Now, if you have a one form such that the periods on any one cycle are integral, it automatically means that it's flat. So here's the idea. You have one cycle here and you deform it slightly, as we did for the symmetry. Because this has to be quantized, it will be an integer, the holonomy cannot change. So the integral of A here and the integral of A here have to agree. But of course, you take the difference of these two integrals. There will be the integral in this little ball here of dA, integral B of f. And that tells you that the integral of f on any point in spacetime, on any ball, has to be 0. So when I wrote flat, I was motivated by what I did there. But in fact, as soon as I impose that these things are integrally quantized with fixed integral quantization, these things are automatically flat. So I could omit the flat here. Okay. So those were the large gauge transformations. These are these integrally quantized one forms, lambda. They have winding numbers, n different from 0. Now, clearly, ordinary gauge transformations this is also in this set. It's a one form. It has integrally quantized periods. just 0. Right?
Sorry again, can you write with bigger?
Oh, yeah, thank you. Let me rewrite this bigger. Okay, so lambda equal to the alpha. This does belong to omega 1, 2 pi z, but the period is just 0. If I integrate this on any S1, I will get 0 by Stokes, as I just said. Okay, so after this discussion, I end up with a statement that gauge transformations this is very bad, isn't it? Okay, maybe this is less noisy. Gauge transforms are elements of omega 1, 2 pi z. So the space of gauge transformations is the space of this group, if I include the large gauge transformations. Okay, so what's the space of symmetries? It's going to be the space of closed forms modulo the gauge transformations. So closed one form, so I'm going to write it like this. Modulo and this means closed. Bless you. Okay, let's think for a bit more about what this is. This one we understand. These are the one forms that you integrate and you get integral periods. These ones are closed, and that means that they're measured by holonomies, right? If you have a one cycle here and some other one cycle here, and they're connected by some two cycles somewhere, then the integral of something close and the integral of something close here are going to be the same. Again by Stokes. Sorry, maybe I should. This is n1, this is n2, and this is m, as before. The integral of n1 minus the integral of n2 on lambda is going to be the integral of m of d lambda, and that's 0. So if you have holonomies, so if you have this kind of one forms, you can tell me what they are. You can specify them by giving me the integral on these one cycles. And the answer for any one cycle that's connected to any other one cycle through a chain of this type is going to be the same. Now, how many of you know what cohomology is? Cohomology. Yeah. How many of you don't know what cohomology is? Again, there's no pressure. Okay, fantastic. Yeah. Of those that know what cohomology is, do you know what singular cohomology is? Which one of you know what singular cohomology is? Okay. I assume the ones that don't know what singular cohomology is, you have seen the RAM cohomology, correct? I know where I am. Okay, very good. So let me introduce very quickly the notion of cohomology. We'll revisit this in the next lecture. I will need a more powerful version, but for today, I can introduce a very elementary version. Actually, if I what I want to say right now, it will be enough to discuss homology, which is a bit easier to picture. All right. So, definition. A cycle in M is a submanifold without boundaries. I'm sweeping under the rug a lot of mathematical subtleties, so assume here that everything is smooth, nice. Just trying to give you intuition. In the next lecture, I'll give something a bit more solid or robust. But for the moment, this is not. So a cycle is going to be as a submanifold of some dimension without boundary. And then the definition, the nth homology group of my manifold is defined to be as cycles of dimension n modulo those that are boundaries. So if a manifold is the boundary of something else, we declare that it's trivial in this group. So here's an important relation. So if I have a manifold M here, and it's the boundary of some n, then this implies that the class of M in Hn, oh, sorry. Okay, let me call this A and B. So A is the boundary of B. The class of A in Hn of M is 0. Okay, so modulo means that anything that is a boundary you identify with 0 as an algebraic object. Another consequence of this definition is that if you have two submanifolds related by a third, like in that picture, that's why I'm going here. This is A, B, and this is C. If the boundary of C is A minus B, then the class of A is equal to the class of B. So if you like, this is a way of having some ambient space M, impose a huge set of relations between all the possible submanifolds I can construct in such a way that I end up with just a little bit of information. Let's do a little bit of some examples. Let's study H0 of a manifold. Okay, so what are the zero-dimensional manifolds that I can construct? Those are points. Right? Now, if I have in some manifold any 2 points inside the same manifold, so this is point, oh, sorry, it's probably too small. Point 1 and point 2. I can construct some curve between them if the manifold has only one component. That tells me that the class of point 1 is equal to the class of point 2. Because the boundary of gamma is 0.1 minus 0.2. Okay. This is if I choose my points to have opposite orientation, if this is plus and this is minus. If I have the same orientation, then I cannot construct a boundary, so a chain whose boundary is undefined. I cannot construct a manifold with boundaries whose boundaries are P1 plus P2. Right? So any 2 points are in the same class, but n points, the class of n points is n time the class of a point. And again, all the points can be connected to each other through boundaries, so it doesn't matter where you put them. The only thing that you have is how many points do you have. So H0 of a manifold is going to be set, that tells me how much n is, to the number of components of m. You have a factor of z for each component of m. If M is a manifold that has 3 pieces, you cannot connect points in one piece to points in another. So that gives you a different factor of Z. Okay, that's all I want to say today about cohomology, just to give you a little bit of intuition. The point is that these relations for flat connections, you see now that they naturally live in a space that associates to every element of H1, any curve, a phase. So we have a U1 phase. Okay, let's go through this once more because that was a little bit quick. I'm trying to use this idea of cohomology that tells me that I can identify, once I use this construction, any two one cycles that are related by a two cycle in this way, as the same object in this algebraic group. And the idea that I'm computing the holonomies for this symmetry generator on one cycles. The holonomy is going to be the same if these two things are related by holonomy. That means that the holonomy is only a function of the class in the homology group. Right. Now, this is this top bit here, saying that the holonomy is a function of the class in the homology group. I'm dividing by the integral ones, and that gives me the U1 structure. In principle, lambda doesn't have to be in U1. This is any holonomy I want. It's the integral of one form. It can be any real number, but because I'm quotienting by the integrally quantized ones, I get a natural structure, which is the reals modulo the integers. That's U1. Okay, so basically, one subtlety I'm not telling you here about torsion, but assume there's no torsion. Then for each one cycle, you get a U1. That's going to be the intuition. Okay. So we always talk about symmetry groups as being U1, but we see that because we are talking about topological operators, the thing we want to classify is how many topological operators we have, and this is how many you have. Okay, any questions? I forgot already. When am I supposed to stop? 45. 45 past or in 45 minutes? I can go on for in 15 minutes, okay. All right. All right, so I recognize this was a little bit quick. In the next lecture, I will develop this much more systematically, maybe in the next, in 2 lectures from now. But for the moment, let it rest. I'm going to try to develop the same kind of thing I did for the ordinary symmetries in this more general case. So what's the Noether's current? All right, well, I wrote the action there. So let's write the action integrating by parts in the following way. And then if I do A goes to A plus lambda, one of these lambdas, I get that S goes to S plus 1 over 2 E squared integral of lambda wedge d star f. So this implies that my J is equal up to constants, which don't matter, star f. So this is a, because there's going to be a magnetic current later, I'm going to call this GE, sorry, for electric current. So I can integrate, so this is a two form, of course. So I can integrate J electric on a two manifold. To obtain something I'm going to call E is parameterized by a parameter alpha and my two manifold, sigma. And this is the exponential of I alpha integral of J E, which is the exponential of I alpha integral of star f, and everything on sigma. Okay. Any questions? So that was very quick, because now we have all the technology in place. The thing that's perhaps not so obvious is to find what are the operators which are charged under this symmetry generator. So the charge operators is going to state what they are, and then we show that they are charged indeed. So these are going to be something known as Wilson lines. I'm going to denote them by W with some charge Q on some curve gamma. So that's a curve. And the definition of this object is that it's the exponential of e to the iq integral over gamma of A. So clearly, under the symmetry A goes to A plus lambda, we have WQ of gamma goes to WQ of gamma times a phase, which is e to the I q integral over gamma of lambda. So this object is charged, but let's make sure that it's actually well defined. First of all, I would like to be invariant under small gauge transformations. I call small gauge transformations those that are of the form d alpha. So I would like my operators in the theory to be gauge invariant. This is no exception. So in this case, what do I get? D alpha. So this is the same thing by Stokes as Q boundary of gamma times alpha. I can choose alpha as I like. So for this to be invariant, I require that the boundary of gamma is 0. I'm not still completely out of danger, still in the danger zone, and that's because I still have large case transformations to worry about. So assume that gamma doesn't have a boundary, and let's think about large case transformations. So my Q of lambda goes to omega Q of lambda times e to the I Q and some integer, so 2 pi times some integer. So invariance implies that Q, again, n is arbitrary, implies that Q has to be an integer. There's a way of understanding this last condition in a way that's nicer and it's physically more meaningful, which is the following. If the gamma where you want to define this is the boundary of some surface, sigma, then I can give an alternative definition of omega q. Now in terms of sigma, which is the exponential of I q integral over sigma of f. Yeah. Again, I'm using Stokes. F is dA. I put the d here, it becomes the boundary. I get that. All right, so choose to sigma and sigma prime such that the boundary of sigma is the same as the boundary of sigma prime. So typically you have many choices for manifolds with a given boundary. So pick 2. Then you compute the difference between these two operators, more precisely 1 times the adjoint of the other. You get the exponential of IQ in sigma minus sigma prime of F. Okay, so the picture here is that we have a gamma, we have a sigma prime, which has the same boundary, and we glue them. If you construct sigma minus sigma prime, now you have no boundary, same construction we had before. So this is going to be some manifold, I don't know, x. This is the exponential of IQ integral over x of F. Now the integral of, in Maxwell theory, we take the integral of F over x to be quantized as 2 pi over z. So this is a standard choice of quantization. It's not really the only choice, but it's the standard choice. So if you choose this standard choice, then this number is generically different from 1 if q is not an integer. So you have 2 pi times I times an integer times q. Unless q is an integer, this won't be 1 for all integrals of f. So what this means is that this operator that I call omega q of sigma depends on the choice of extension for q non-integral. I want to emphasize that this is fine. All we are saying here is that we have an open operator. So we have some operator like this with a boundary, and on the bulk we have some extra piece attached to it. And I'm saying that we need to specify what this piece is. So this operator doesn't make sense as an operator defined on curves, but it makes sense as an operator defined on open surfaces. It's sometimes very useful to think of these non-integrally quantized open surfaces, so that's why I emphasize this point. So let's think of this operator for a minute. This is the e to the I bit here. This is the Wilson line. And then we have something which is the, here, we have the exponential of I q integral over this surface, sigma of f. Let me give this a name. I'm going to call this m q sigma. Is this big enough? Sorry, I'm a little bit paranoid. So you have this operator here. The half is defined. And note that d of f in this abelian theory is d of dA, the square of a, 0. So we just found another topological operator. So I'll have much more to say about this one in the next lecture. Okay, perhaps this is a good point to stop. So I'll see you tomorrow.